This is video 5.2. It deals with electromagnetic waves, a very useful family of waves indeed. We humans use all of them for all sorts of things. Broadly speaking, we'll start at radio and work our way through. As you can see here, frequency gets higher, so gamma has a very high frequency and a very short wavelength. We'll try and make it relevant to everyday objects, and we'll try and think about the wavelengths and frequencies again in a bit more detail, but the main thrust will be about the uses. So over here, communication is a really key one, a huge one here. So radio, remote control, optical fibres, mobile, satellites, a huge range of applications there. Cooking is another one, lasers, which comes into communication, but lots of other things as well. Imaging of all kinds. We do have some uses of ultraviolet, killing bacteria, tanning, security features, then medical imaging and medical treatment to finish off with these high energy ones here. Now these three, as you can see here, are dangerous. All can be dangerous if strong enough, but these are the key ones to be aware of. So briefly, they're all around us. As we said, our living rooms are full of devices, Wi-Fi, radio, TV, a huge amount these days, and I'm sure this is fairly typical. So all these electromagnetic waves have one thing in common: they have the same velocity, and it's incredibly quick. It's about 10 times around the world in a second, which is incredibly useful to us because we want things to be transmitted quickly. So here we've got a representation of what they actually look like. So they've got an electrical component and a magnetic component. They're at 90 degrees to each other, and they transfer energy. Sometimes they transfer information as well. In our example here, we've got a solar energy station. So all these reflectors are sending the heat and the light back up to these towers here, and they're creating steam. Now here we've got a table showing us, or emphasizing again, that they all have the same speed. It's a common mistake, but they do always have the same speed. In a vacuum, it does change slightly when they go into solids, as we'll see in a second. So wavelengths vary hugely. So radio waves can be actually more than this, up to 1 kilometer, and it's already quite difficult to visualize these kinds of distances. But infrared is less than a millimeter. Visible, we're talking hundreds of nanometers, nano meaning billionth, and then a gamma, as we said, very, very small indeed, and the frequency is getting correspondingly larger. So this column multiplied by this column always equals this column, which is our formula here, V equals F lambda. So to give this a little bit more of a sense of scale, if we can, so radio, size of buildings, microwaves can be 10 centimeters or so, infrared, millimeters, so the size of a needle. Here it gets harder because not many have a huge sense of how big a protozoan is, but pretty small, and molecules, ultraviolet, X-rays can be used to examine atoms, and gamma rays smaller still. So radio, the thing we're most familiar with, obviously, is communication. So radio for shipping or entertainment or broadcast. What's going on here is that an electron, a current in the mast, is going up and down. This creates the wave. It's sent out, and it does creates the corresponding motion in an electron in the antenna, and that's massively boosted or amplified by the radio and then turned into sound. So here in food, it's the energy we're interested in transmitting. So a grill will use infrared. So it's a modern version of a fire, in essence, the thing that's transferring the heat. Microwaves are particularly sensitively tuned to water, and they are designed to transfer energy very efficiently, and they can penetrate further, and this is the key reason why they're quicker. They can penetrate a few centimeters into the food and start directly heating it, whereas infrared has to rely on conduction once it's got to the surface. So visible light, we've evolved to be sensitive to the radiation that gets through our atmosphere. It makes sense that we should be sensitive to that, although we put lots of telescopes up higher to avoid this absorption. So if we're interested in X-ray, we have to go above the atmosphere because it blocks a lot. Now, within this range, various animals have evolved to either use infrared. So here's a rattlesnake. Now it has these heat pits, they're sometimes called. You can call it a second pair of eyes if you like. And a bee can, so this is what we would see, the yellow flower, but it sees these landing strips to tell it where the nectar is. It's kind of an advertisement. But the real champion is the mantis shrimp. Has an astonishing range of vision, both into UV and into infrared. So optical fibres, whenever we make a mobile phone call to the other side of the world, let's say this is what happens. Your J, let's say, gets encoded into a number and then into binary, which is a form of numbers which only has ones and zeros. That's transferred into ons and offs to the local mast. Now that might be only a kilometre or so. Then it's transferred into optical fibres. Optical fibres run all over the oceans, also over the land, and then it finds the mobile you're trying to reach. Now the key thing here is something called total internal reflection, and that only happens after a certain angle. So here we've got refraction, where the small dotted line or the ray is going in to our substance here, but beyond a certain angle into the green, as soon as we're into the green, these longer dashes will actually reflect, and that's a property that optical fibres exploit. They can be used for all sorts of things, cutting, recording information, surgery, and weapons nowadays as well. The essence of it is just normal light. It's just very ordered, and you can see here in our animation that all the peaks line up, and they all have exactly the same frequency, and it makes for a very intense source of energy. So here we have ultraviolet. Ultraviolet is used for tanning, and it's used for security devices. What's happening here is that the ultraviolet is hitting a particular chemical, and the chemical is turning that into visible light. So when we put ultraviolet on certain chemicals, it turns into visible, so we can see things we normally can't. Now we did mention dangers earlier, so the higher the frequency, the more dangerous it is, and the further it will penetrate and the more damage it will do to skin. So the outside of the skin is dead cells, can't become cancerous, but the living cells, if it penetrates further in, it can have severe effects. Medical imaging is a very important use of EM waves. So here we've got infrared, we can see there's some kind of inflammation. X-rays we're very familiar with, and then gamma we're less familiar with. So let's look at those last two in a bit more detail. So here's an X-ray machine. We've got electrons. They come off a kind of element here which gets quite hot and sort of boils off the electrons. They're accelerated at a very high speed to this target. When they hit the target, they produce this very, very high frequency type of electromagnetic wave, X-rays, and they can fly through this bone section. Think this is a leg. The bone is dense, so it will absorb. You can see they're being absorbed here, but where it misses the bone, it will largely pass through, and that creates the shadow picture which we know of as an X-ray. It produces a very high resolution picture, although it does have some dangers associated with it. Then we have gamma imaging. So here a substance is injected into the patient which has gamma radioactivity associated with it. It'll concentrate in the area where the problem is, and the gamma emitted is then detected, and we can see where the problem is. So here's a real image, and you can see that it's highlighting particular points on the body where inflammation or some problem has occurred. Lastly then, astronomy uses the whole of the electromagnetic spectrum, and so this is the same remnant. This is a supernova, an exploded star that's now thousands of years old, but we can still learn a lot from it. You can see how different it looks and how different aspects of it are being revealed by looking at the different parts of the EM spectrum.